Yeah, put on your investigative hat today because we got to get down to business and we're going to solve some crime scene problems today. So our theme today is Newton's law of cooling, and it is a big bear to say the least. And I want to introduce you to a question that it's our goal to be able to solve this question by the end of the video tonight. It says a crime scene investigator arrives at the scene of a crime where the dead body has been found. He arrives at the scene and measures the temperature of the dead body at 9:30 with a temperature of 78.3 degrees Fahrenheit. He checks the thermostat and determines that the temperature of the room has been kept at 74 degrees Fahrenheit. An hour later at 10:30, the investigator remeasures the temperature of the body again. It's now 76.8 degrees Fahrenheit. Now he assumes the initial temperature of the body was 98.6, which is normal body temperature, and our goal is this. Using this data, the crime scene investigator proceeds to calculate the time of death. According to the data he collected, what time did the person die? Now, basically, without actually solving the problem totally yet, here's what's happening, okay? The outside temperature, or the temperature of the environment here, is 74 degrees, and that's the air surrounding the dead body. And so what that does is creates this asymptote. Now, the body was originally 98.6, okay? And then if t equals 0 represents when the person died, the body's temperature is going to slowly approach 74 and forever get closer and closer. And see, what you have here is an exponential model, specifically exponential decay, and that's why this topic fits so nicely with what we've been studying lately. So back to the drawing board here, we're going to hit the reset button and we're going to kind of build up to the point where hopefully by the end of the video we can come back and answer that crime scene question. So first things first, I just want you to solve for k, okay? Can we isolate k? Can we find the value of k? I don't want you to worry about where the numbers came from or anything yet. Let's just see if we can use our math skills to solve for k. And a couple of things that may catch your eye right off the bat here is I think we could combine these two terms together. And at the same time, I'm going to go ahead and I'm going to subtract this 21 to the other side. So I've got 64 equals, and then if I subtract this 101 and the 21, I should get 80 times e to the negative 4k power. Now ultimately my goal is to try to isolate what we call the exponential term, okay? And I'm going to put some red parentheses around that term. That's what I call the exponential term. And so in order to isolate that term, I'm going to divide both sides by what? Yeah, let's divide both sides by 80. Conveniently, 64 divided by 80 turned out to be a very nice decimal, 0.8. And if you recall there before, and in one of our previous lessons, we said if we're solving for a variable, in this case k, that's part of the exponent, at some point we're going to take the log of both sides. Now you could take log base 10 of both sides, you could take log base 2, but I'm going to choose log base e, or in other words, I'm going to take the natural log of both sides. And let's see, e to the negative 4k. Whatever we do to one side, we've got to do to the other. Now, I'm going to use one of my log properties, specifically the third log property called the power rule, that says this exponent can move to the front. So I've got negative 4k multiplied by the natural log of e. Now this is real slick here. If you recall, and we'll make a little note here off to the side, that the natural log of e equals 1. And the reason is as we're reading this, we're thinking, what power of e is e? And the answer is 1. So this term right here is just a 1. So I've got the natural log of 0.8 equals negative 4k. Divide both sides by negative 4. And let's see, I got k equals, and I'm just going to print all the decimals here off my calculator screen. 0.557858878. And then from there we could determine what we want to round to based on the directions. Okay, now we're going to get real specific and try to introduce you to Newton's law of cooling. And Newton's law of cooling is used to model. Boy, there's a buzzword we're going to see more and more of as the year goes on. Model the temperature of an object, aka a dead body, of some temperature placed in an environment of a different temperature. So, initially the dead body started out at 98.6, but the room temperature was 74, aka a different temperature. And what happened was the temperature of the dead body slowly got closer and closer to the temperature of the room. And the temperature of that object, T hours after being placed in the new environment, is modeled by this formula right here. So we're going to spend the rest of the video talking about how to interpret this formula, what each of these crazy letters means, and then practice some word problems where we're just plugging numbers in and solving for, whether sometimes we solve for k, sometimes it's a lowercase t, whatever the case might be. Okay, so let's introduce you to each of these letters. Now, a lot of times what we have right here, where we say capital T of lowercase t, sometimes you'll just see the formula written as a capital T equals. So I'm going to go from left to right and introduce you to each of these variables. The capital T without a subscript of any kind is the temperature of the object after T hours. The temperature of the object, aka dead body, after T hours. Okay, capital T with a subscript of A, and actually the A represents ambient, and we're going to define that as the temperature surrounding the object. The temperature surrounding the object. In this case, in our first example, this would be the temperature of the room with which the dead body was in. So we call it the ambient temperature sometimes, or just the temperature of the environment around the body. The next thing, let's introduce you to capital T with a subscript of O, or subscript 0. This represents the initial temperature of the object. Okay, we're almost getting there. Then the next thing we see is, now the letter E is Euler's number. Remember that? And we did a really good job of pronouncing it correctly the other day. Now remember, Euler's number is a constant, and sometimes we'll use the word parameter instead of constant, okay, just so they all mean the same thing. So, but know this, that the letter E is a parameter, it's a constant. The next thing up there is a k, a lowercase k. This represents what we call the decay constant. That'll dictate typically at what rate it's decaying. And then the last thing is lowercase t, and this is the time in hours. Now I guess, that's going to change from problem to problem. It's not always going to be hours, okay? This could be minutes, it could be seconds, it could be days, but it'll be some measurement of time. So here's a thought-provoking question. They said, assuming that the temperature of the object is greater than the temperature of the environment, is this formula an example of exponential growth or exponential decay? And I think to give ourselves a little visual image, and hopefully you've kind of got an answer already in your back pocket here. So picture the CSI problem we looked at where we said, okay, here's the room temperature, or the temperature of the environment, and we said here's the initial temperature of the object, and how that's going to decrease and approach but never actually touch that asymptote. So I think the picture clearly illustrates, and again, let's do this. Let's say this red line represents T sub A, and the first blue dot is T sub O. And so this clearly looks like exponential decay because the function's decreasing. Here's another thought-provoking question. They said, well, why would it be decay when the base of E is greater than 1? Do you remember we used to say, this was our generic form that we initially started with, and we said as long as B is greater than 1, the function's going to increase or grow, and if 0 is less than B, which is less than 1, then the function's going to decrease or decay. Okay, so this seems to violate or contradict what we have here, because over here, my base is E, and we know that E is approximately 2.718, yada, yada, yada. So, but what's really happening is this E is being raised to the negative K, which is equivalent to 1 divided by E raised to the K power. So really what we're saying is your base here is 1 divided by E, which is clearly less than 1, which is the real ultimate reason why it's decaying as opposed to growing. All right, it's time to dive in here. So let's get our first live example. So here, Instead of thinking of a dead body here, let's think of a pot of tea. Now, we heated up a pot of tea to 90 degrees Celsius. Put a little degree sign there. Now, that cup of tea is poured into a mug and taken outside where the temperature is 18 degrees Celsius. And after 2 minutes, the temperature of the cup had already dropped from 90 down to 65 degrees. So their first question here is determine the value of the decay constant, also known as K. So our goal here is to solve for K. And what I did is did a little copy and paste of what we already had put in our notebook as far as defining all the crazy variables within Newton's law of cooling formula. And we're going to try to assign each of these rascals. So as far as capital T goes, the temperature of the object after T hours, in this case it's after 2 minutes, so everything's in minutes here, but that would be 65 degrees Celsius. What was our ambient temperature, the temperature surrounding the object? Well, that would be our outside temperature of 18 degrees Celsius. The initial temperature of the object was the 90 degrees. Euler is a constant. K is what we're solving for. And then the last one is that little t, and that would be 2 minutes after we remeasured the temperature. So let's see if we can get everything plugged in here, and then we'll talk about solving for K. So I'm going to substitute the 65 for capital T, and then 18 for T sub A. In parentheses, I've got the original temperature minus the ambient temperature. And that's being multiplied by e raised to the negative 2 times k. So I substituted the 2 for the lowercase t, and I got that. So again, we're solving for k. So let's see what we did. Very similar mathematically to what we did on the opening slide. I'm going to go ahead and I'm going to subtract 18 from both sides. That gives me 47 equals, and then at the same time I'll combine these two terms to make 72 times e to the negative 2k. My next move is to divide by 72. Unfortunately, this didn't give me as friendly of a number. It gave me a decimal 0.6527 with the 7 repeating. And that equals e to the negative 2k. Now that we've isolated our exponential term here, we're going to go ahead and take the natural log of both sides. And on my calculator, I've got this 0.6527 repeating number stored. Let's see. I'm going to grab that exponent and I'm going to move it out in front. One step at a time, right? Nice and easy, one step at a time. Negative 2 times k times the natural log of e. One of my favorite moves. We know that the natural log of e is just 1. So I'm going to go ahead and I'm going to divide both sides by negative 2, and I should have it. As I'm punching that into my calculator, I got k equals 0.213. So anyway, let's go 3 decimals right here, and we'll carry these 3 decimals with us as we answer a few more questions that pertain to this scenario. So here they want me to write a function for the temperature of the tea in the mug, represented by capital T. Now just to recap what Newton's formula says is he says capital T is going to be T sub A plus, let's see, T sub O plus T sub A times e to the negative kt. The k is not showing too good. Anyway, so if I plug everything in as I know it, we know that the ambient temperature was 18. And then we did 90 minus 18 to get 72. And now we've got e raised to the negative 0.213 t power. So that's the equation. Now as far as graphing that function goes, we know that there's got to be a horizontal asymptote at 18 because that's the ambient temperature, and that's going to be true every time. So I'm going to approximate where my 18 is, and I'll put my horizontal asymptote. I'm going to label it y equals 18. And what I'm going to do over here is I'm going to put a little t with a subscript of a just to remind myself that the ambient temperature. Now my initial temperature was 90 degrees, and from there I know the function's going to decay or decrease and trend right into that asymptote. So this is a sketch of what capital T of t, the function t, would look like. This might perhaps be the most challenging little mini exercise of the night. They said they want you to use our properties of exponents to rewrite the temperature function in this form right here. In other words, Right now, the function we have, our base is e. They want me to rewrite it so that the base is written as 1 plus r raised to the t power. So we've really got to get rid of this rascal. And so what I'm going to do is I'm going to group this guy together first. And I'm just going to type that into my calculator, okay? Now, as I type that in, and I'm just going to kind of off to the side here show some of my work, is e raised to the negative 0.213. My calculator gave me 0.808, etc., etc., etc. So I'm going to insert that. And so we know capital T of t is really 18 plus 72 times 0.808, etc., etc., to the t power. So the good thing is we've got the power down to just t, but now I want to do 1 plus something. So the question is, 1 plus what would be equivalent to 0.808? I'm going to put a little question mark there. So 1 plus something, this is what I'm thinking, 1 plus something equals 0.808. All I got to do is just subtract 1 from both sides, and we'll figure out that that mysterious something is 0.192. So let's rewrite this one last time and say the temperature of the T is 18 plus 72 times the quantity 1 plus a negative point, whoops, I don't know if I got my negative there, 0.192 raised to the T power. Now what was the advantage of that? Well, that was just to set us up for this next question here. What's the percent change per minute? Now the whole idea of this per minute implies that the exponent had to be a 1. If this exponent right here wasn't a 1, we wouldn't be able to do per minute on an annual basis, right? This goes back to our whole idea of annual change. So the percent change is just going to be, I'm going to move that decimal twice, and I'm going to say, well, it's decreasing, the temperature is decreasing at a rate of 19.2% per minute. Well, we haven't done too many examples, but I tell you what, we're going to try to wrap it up here with this pizza problem. And I tell you, I wouldn't be surprised if you could hit the pause button, set this bear up all by yourselves, and really solve this problem without me getting too involved here. That would be the goal. So I would challenge you to do that right now. So my thought process goes like this. Now, this 400 was the initial temperature of the pizza, T sub O. It was then taken out of the oven and placed in a room at 75 degrees Fahrenheit. So I'm thinking T sub A, the ambient temperature, is 75 degrees Fahrenheit at T sub 0. Now they said the temperature of the pizza is changing such that its decay constant is going to be 0.325. Okay, at what time is the temperature of the pizza at 150 degrees? So here's the deal. Little t is a question mark. Capital T is 150 degrees Fahrenheit. So in this time, instead of solving for k, we know what the value of k is. We need to solve for lowercase t. Let me recopy Newton's formula here. And let's see, T sub A plus the T sub O minus T sub A. I haven't used this formula too much, and I'm already starting to get it memorized and get the hang of it here. So we got a 150 here, ambient temperature, and then 400 minus 75, and this would be E raised to the negative 0.325 lowercase t power. Okay, mathematically, let's subtract 75 from both sides. And that's going to give me 75 equals 325 e to the negative 0.325 t power. Let's divide both sides by 325. I think of all the things we're doing today, this is right in our wheelhouse. This is where we feel the most confident. 0.2307, yada, yada, yada. And I did store that number as alpha A, and that equals e to the negative 0.325 lowercase t power. Let's take the natural log of both sides. And as I'm doing that, I'm going to go ahead and move my exponent in front of the log. My favorite part here, we know that the natural log of e is simply 1, so let's go ahead and just simply divide both sides by the coefficient negative 0.325. Calculators, the MVP today, going to do some nasty number crunching here on the calculator. I got 4.5, whoops, said 5, wrote a 4 though, 11 equals t. So let's interpret that. What does that represent? Well, it's going to take about 4.5 minutes in order for that pizza to cool down to a temperature of 150 degrees where you might start to think about taking a bite without burning your tongue, hopefully. So about 4.5 minutes before it can cool down. So great job today. Good job hanging in there. We'll do a lot of practice with Newtons, and we'll come back to that dead body problem and try to determine the time of death.